In the grand cosmic theater, the script seemed elegantly simple, written in the language of physics and confirmed by the light of distant stars. Following the revelation of the Big Bang, we came to understand our universe as a place of majestic, orderly expansion. The prevailing narrative, etched into the bedrock of 20th century cosmology, was that of the Hubble flow. It was a cosmic diaspora in which every galaxy, every cluster, every supercluster was receding from every other, carried outward on the swelling currents of space-time itself. The farther away a galaxy was, the faster it appeared to flee. This was the cosmic standard, a universal rule that brought a comforting sense of order to the celestial chaos. Our own Milky Way, we presumed, was simply a passenger on this great, expanding tide, its motion dictated by this single, overarching principle. This beautiful simplicity was, in large part, built upon a single, profound observation: the cosmic microwave background, or CMB. This faint, pervasive glow of radiation, detectable in every direction we point our instruments, is the universe's oldest light. The fossilized echo of the Big Bang itself, in its near-perfect uniformity, with a temperature hovering just 2.7 degrees above absolute zero. The CMB provided cosmologists with the ultimate frame of reference. It was the stationary backdrop against which all cosmic motion could be measured, a silent testament to the universe's primordial state. Any deviation from this perfect stillness would be a story in itself. And in the 1970s, as our instruments grew more sensitive, we began to read a startling new chapter in that story. The anomaly didn't arrive as a cataclysmic discovery, but as a subtle, persistent whisper in the data. Our telescopic observations of the CMB revealed a faint, yet unmistakable pattern known as a dipole anisotropy. One half of the sky appeared infinitesimally warmer, its light slightly blue-shifted, while the opposite hemisphere was infinitesimally cooler, its light red-shifted. The physics was undeniable. This was the signature of our own motion. It was a cosmic Doppler effect, proving that we were not merely passive riders on the Hubble flow. Our entire local group of galaxies, the Milky Way, Andromeda, and dozens of smaller companions, was hurtling through the universe at a staggering speed. The numbers were almost incomprehensible. After accounting for the Earth's orbit around the Sun and the Sun's journey around the galactic core, a residual velocity remained. We are moving at approximately 600 kilometers per second, over 2 million kilometers per hour, relative to the rest frame of the universe itself. This was a profound scientific paradox. The foundational model of cosmology described a uniform expansion, yet here was concrete evidence of a powerful, directional, peculiar velocity. An enormous cosmic current pulling us toward a very specific point in the sky. It was as if we were on a perfectly calm night, only to find ourselves being dragged by an invisible undertow toward an unseen shore. Gravity is the only force capable of orchestrating such a colossal motion across such vast distances. The implication was as immediate as it was unsettling. Something was out there. Something immense, a concentration of mass thousands of times greater than our own Milky Way, was exerting a gravitational pull that was powerful enough to defy the universal expansion. We couldn't see it, we had no name for it, but we could feel its influence, a steady, inexorable summons across hundreds of millions of light years. The hunt had begun for an object or a structure that was a ghost in the light, but a giant in the dark. It was the first hint of a hidden architecture in the cosmos, a force that would come to be known only by its effect: the Great Attractor. Knowing the direction of the pull was one thing. Identifying its source was a challenge of a different order entirely. The cosmic velocity vector pointed unequivocally toward a patch of sky spanning the southern constellations of Centaurus and Norma. Yet, when astronomers aimed their optical telescopes at this region, they were met with an unnerving silence. There was no single titanic galaxy, no uniquely brilliant quasar, nothing that visually announced itself as a gravitational monarch capable of commanding the motion of 1,000,000 billion suns. The culprit, it seemed, was hiding in plain sight, yet remained perfectly invisible. The reason for this maddening cosmic paradox lay not in the distant target, but in our own home. Our line of sight to this gravitational anomaly was aimed directly through the densest part of our own galaxy, the galactic plane. This obstructive band is known to astronomers as the zone of avoidance. The name is not an admission of cosmic emptiness, but a confession of observational blindness. This region, the glowing disk of the Milky Way, is a formidable barrier of stars, incandescent gas, and, most critically, vast clouds of interstellar dust. This cosmic dust acts as a thick, impenetrable fog, absorbing and scattering the visible light from distant galaxies, effectively wiping them from our sky. For decades, maps of the universe had this glaring, empty stripe across them, a testament to our limited vision. And with a sense of cosmic irony, the Great Attractor was located squarely in the middle of this blind spot. We were trying to solve a mystery by looking for clues buried under our own front porch. To pierce this stellar veil, science required a new way of seeing. The solution lay in escaping the narrow confines of the visible spectrum and deploying instruments sensitive to wavelengths of light that could navigate the galactic fog. Infrared astronomy provided the first breakthrough. With its longer wavelengths, infrared light is far less susceptible to scattering by interstellar dust. Groundbreaking infrared surveys began to peel back the layers of the zone of avoidance, revealing the faint, ghostly outlines of countless galaxies that had been hidden for all of human history. These were the first crucial clues. But to confirm their role in the cosmic flow, we needed more than just their location. We needed their velocity. This is where radio astronomy entered the narrative. Using powerful radio telescopes like Australia's iconic Parkes Observatory, astronomers tuned in to a specific frequency: the 21-centimeter wavelength emitted by neutral hydrogen gas, a fundamental component of spiral galaxies. These radio waves pass through the Milky Way's dust almost entirely unhindered. For the first time, we could not only detect the galaxies in the zone of avoidance, but by measuring the redshift of their hydrogen signature, we could determine how fast they were moving. The data that poured in was stunning. A vast, previously uncatalogued supercluster of galaxies, the Norma cluster, was uncovered, sitting precisely at the gravitational heart of the mystery. This was no minor collection of galaxies. The Norma cluster, also known as Abell 3627, is a behemoth, a teeming metropolis of galaxies bound together by their mutual gravity. To appreciate its scale, a task of comparative astrophysics, consider that our own local group, containing the Milky Way and Andromeda, has a mass of perhaps 2 trillion suns. The Norma cluster weighs in at over a quadrillion solar masses, roughly 500 to 1,000 times more massive. Its discovery was a monumental success, a testament to the power of multi-wavelength telescopic data and observation. Here, at last, was a structure with the gravitational heft to be a primary suspect. But this discovery also demanded a crucial act of myth-busting. The name, the Great Attractor, had conjured sensational images of a cosmic vacuum cleaner, a singular object like a universe-sized black hole inexorably sucking us toward our doom. The reality is far more subtle. It is not a thing but a place. The Great Attractor is a broad, diffuse region of overdensity, a valley in the fabric of space-time into which our corner of the universe is slowly flowing. A galaxy cluster is a massive concentration of matter within that valley, but it is not the entirety of the attractor itself. The Norma cluster is a massive concentration of matter within that valley, but it is not the entirety of the attractor itself. We are not on a collision course to be devoured. We are simply following the gentlest of cosmic gradients, a path dictated by the sum of all the matter in our vicinity. And even with this clarification, the numbers still didn't add up. When physicists calculated the total mass of the Norma cluster and its surrounding structures, they found it could only account for about half, perhaps a little more, of our observed 600 km/s motion. A significant portion of the gravitational pull remained unexplained. The primary suspect was in custody, but it clearly had accomplices. The search expanded once more, this time into the high-energy realm of X-rays. Giant clusters of galaxies are filled with superheated gas that glows brilliantly in X-ray light, making them impossible to miss. X-ray surveys confirmed the scale of Norma, but also began to reveal an even larger tapestry of structures, a web of clusters and filaments extending far beyond the original search area.
I've got the coordinates.
The investigation had revealed that the Great Attractor was not an object to be found.
Are you sure about this?
But a hierarchy of structures to be mapped, an architecture whose true, magnificent scale was only just beginning to come into focus. The incomplete answer provided by the Norma cluster forced a profound shift in scientific thinking. The hunt for a single, discrete object was over. The mystery of the Great Attractor was clearly a question of mapping a complex, hierarchical structure on a scale never before attempted. The challenge was no longer to find a single culprit, but to chart the boundaries of our own gravitational domain. To draw the lines on a map that would finally tell us where we truly belong. The answer, when it came, was more elegant and awe-inspiring than anyone had anticipated. It didn't just solve the puzzle of our peculiar velocity. It fundamentally redefined our cosmic address. The breakthrough came from a new way of visualizing the cosmos. A team led by astronomer Brent Tully compiled a comprehensive catalog of the motions of over 8,000 galaxies in our local universe. Instead of just plotting their positions, they mapped their velocities, tracing the paths they followed along the invisible contours of space-time. Their technique allowed them to delineate gravitational watersheds, vast cosmic basins of attraction. Just as rain falling on a continent will inevitably flow toward a single river valley, they could now see which galaxies were flowing together toward a common gravitational center. What their map revealed was a single, coherent superstructure. We were not being pulled by some external force. We were already inside the house. This structure is our home supercluster, a colossal filament of the cosmic web. That was given the Hawaiian name Laniakea, meaning immeasurable heaven. Laniakea is a staggering entity, spanning over 520 million light-years and containing the mass of 100 quadrillion suns distributed across 100,000 galaxies. And the Great Attractor. It is simply the gravitational heart of Laniakea. It is the broad, flat river valley toward which all the tributaries of our supercluster flow. Our Milky Way is just one droplet in one of these streams. following a gravitational path of least resistance toward the center of our home. This revelation was a paradigm shift in cosmology. The anomaly that began the search was, in fact, the most powerful evidence of the very system to which we belong. Yet, even this profound discovery was not the end of the story. When astronomers calculated the bulk motion of Laniakea itself, they found that our entire supercluster is also on a journey. The whole magnificent structure, our galaxy, the Great Attractor, all 100,000 members of Laniakea, is being pulled across the universe by something even more massive, lying even further away. The prime candidate for this cosmic tug is the Shapley Supercluster, the most massive concentration of galaxies in the local universe, a gravitational titan exerting its influence from over 650 million light-years away. Here, then, is the grand implication. The search for the Great Attractor unveiled a breathtaking cosmic hierarchy. We live on a planet, in a solar system, in a galaxy. That galaxy is flowing toward the center of the Laniakea Supercluster. And Laniakea itself is flowing toward the Shapley concentration. This raises the human question with renewed urgency. What does it mean to have an address on such a scale? It instills a sense of belonging to a structure of almost spiritual magnificence. The Great Attractor is not a destination we fear, but a signpost that helped us map our home. It taught us that the universe is not a static collection of islands, but a single, interconnected ocean of currents and flows. And as we gaze out beyond Shapley, we are left to wonder, is that the final shore? Or is it, too, just another current in a river that flows toward an even greater and as yet unknown sea? The mystery continues.